All right, here we are in Chapter 11, an Introduction to Organic Chemistry. So this is the second semester of the full year sequence. This is General Organic and Biological Chemistry 2, Chem 142 here at SUNY Broome. And hopefully we were together for the general part back in Chem 141, but whomever you had, whether it was me or another instructor, hopefully you got a firm foundation in the basis of general chemistry, because we will use those concepts, in particular bonding concepts that you learned back in the first half, in order to tackle the organic and biochemistry that we'll do here in the second half. I know a number of you are out there in the course for hopefully a career in the health professions, and organic and biological chemistry is the more relevant for the health professions, but this first chapter on alkanes is not particularly biologically relevant. Alkanes are relatively simple, and they'll give us a good foundation of what organic chemistry is all about, but there won't be a whole lot of biological relevance in this chapter, but there will be later on in the course, so hopefully just hang in there and we'll get to it to be sure. As I just mentioned in the previous slide, we're going to talk mainly here in this first chapter about alkanes. But before we even go into alkanes, we have to define what an organic compound is in the first place, and why the alkanes qualify, and why, as we'll come to see later on in Chapter 11, why they're a relatively simple example of an organic compound. So just bear with us. We'll get through these first couple chapters, and then we'll be ready to delve into the biological chemistry for those who are headed in the health professions. For those who are in here for the organic, then you're ready to start absorbing all this stuff right away. All right, so by definition, an organic compound typically contains carbon and hydrogen atoms. So it has to have carbon, and usually it has hydrogen as well, but it may also contain other atoms such as oxygen, sulfur, nitrogen, phosphorus, or a halogen, which would be one of those group 7A or 17 elements like fluorine, chlorine, bromine, and iodine. And in particular, in the human body, in terms of organic compounds, we tend to see mostly carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, although we do see chloride and iodide as important ions in general chemistry for human body function. Mainly for the organic compounds, they tend to be more than just carbon and hydrogen in terms of what we use biologically. We see here in the slide an example of propane, C3H8. Some of you likely heat with propane. That's an expensive fuel to use, unfortunately. I know it's typically used in places where natural gas piping hasn't been installed. So it is a fairly expensive fuel to use. So I feel for you, those who are on propane for their heating and cooking. But it is a wonderful example of an organic compound. And you see there it's a carbon, 3 carbons, and 8 hydrogens total. And we see those space-filling models there. We'll get a better sense of what propane looks like as we talk through the rest of this chapter. Looking into some generic properties of organic compounds, again, not all, but many organic compounds are nonpolar. Especially if they're just carbon and hydrogen, then that's not a very big dipole moment, if you remember that argument from way back in GOB1. So they tend to be nonpolar. They tend to have relatively weak attraction between molecules, which is why the smaller examples like methane and ethane are gases at room temperature and pressure. Propane's a gas at room temperature and pressure, but slightly higher pressure or slightly lower temperature we can liquefy it, and that's why in our previous slide we saw propane used as a heating and cooking fuel, because you can transport large amounts of it in the liquid phase. They tend to have low melting and boiling points as a result of those weak intermolecular forces. They're not generally soluble in water, although we'll certainly see classes of organic compounds that do have very good water solubility when we get into discussions of alcohols, for instance. They're usually less dense than water, although there are some really dense organic substances out there. Generally, they tend to be less dense than water. They tend to float on water. As we see in our picture there, we have oil and water. So oils are organic compounds, carbon, hydrogen, oxygen, and then water, of course, H2O. Being a polar substance, doesn't interact well with those non-polar oils, and that's why you get the separation. The oil is the top layer because the organics tend to be less dense than the water layer. Finally, they tend to be highly flammable, especially these alkanes we'll talk about, which is why we use them as fuels, because when we're looking for fuels, we tend to look for something that's flammable. And so things like propane that we saw in the previous example, octane, which is a principal component of gasoline, liquefied gas, we'll see that we tend to look at alkanes for those sorts of applications. And here in table 11.1, we see some typical properties of some organic versus inorganic compounds. Again, these are typical organic and inorganic compounds, but there are exceptions to both. So don't get too attached to these being hard and fast rules, but they are rules of thumb, so to speak. So for organic substances, we tend to be dealing with carbon and hydrogen, and then sometimes some other select elements, whereas in inorganics, we deal with the whole periodic table. So aside from those substances that have only been around for fractions of seconds, the post-uranium elements that are have no stable isotopes, they tend not to be too important in chemistry at the macro scale, but most everybody else there up through uranium is manipulated in the field of inorganic chemistry. For bonding, organic tends to be mostly covalent bonding, which we learned about back in GOB1, Chem 141, so hopefully you still remember those concepts. In the propane that we looked at, we have covalent bonds, 4 bonds to each of those carbons. So the 3 carbons are connected in a chain by one single bond each, and then the 2 carbons at the ends of the chain have 3 hydrogens to complete their 4 bonds, whereas the carbon in the middle has just 2 bonds left to make with hydrogen. So that's how we end up with C3H8 as our formula. For inorganic substances, many are ionic, some are covalent. If we're dealing with the metals, there's metallic bonding, so we get a lot more variety in the inorganic, although we tend to think of them as ionic bonders for the most part. Polarity, we've got nonpolar substances, although we can have significant polarity if we've got an oxygen in there, for instance, which is a very electronegative atom. So we do sometimes get some polarity, and I already mentioned the alcohols as an example of when that happens. When you have the COH bonding, you get quite a polarity of bonds. So it's typically nonpolar, but you can have some polar substances in the organic classification. For inorganics, you tend to get ionic or polar covalent. You get a few nonpolar covalent, but again, by and large, you tend to deal with mostly ionic or polar covalent substances. Melting points of the organics tend to be pretty low because of the types of bondings that we tend to be talking about, and the intermolecular forces tend to be pretty weak, so you get low melting points, low boiling points. The example with propane, we see minus 188 and then minus 42 for the melting and boiling points. For inorganic substances, since we tend to be dealing with ionic or polar covalent bonding, they tend to be a pretty high melting and boiling points. If you look at sodium chloride, 801 degrees Celsius and 1413 degrees Celsius, so definitely solid at room temperature and pressure. Flammability of the organics tends to be high. They tend to burn in air. That's why they're desirable fuels. Inorganics tend to have low flammability. They tend not to burn, so they tend not to be very good fuels. And solubility in water, organics tend to be not soluble unless we have a polar group like an OH group for the alcohols, which have good water solubility up to a point. And then we see, at least for the propane, it's not especially soluble in water, very low, if any, solubility, whereas the inorganics, most are soluble unless they are nonpolar or just an ionic example like we learned in Chem 141. We had things like silver chloride that it's ionic, but it's just not soluble in water. Okay, so sodium chloride, of course, is an example of a soluble inorganic species. All right, so if you've had me for 141 and you took it in the online format, you've gotten used to these learning checks. We talk a little bit, then we see how you're doing on your own. If this is new to you, this is going to be the scheme. So we've had a little time to chat about some key properties of organics and classification of organic versus inorganic. So now you'll go ahead and see how you're doing with these concepts by taking this learning check. So in this example, we're going to identify each of the following characteristics as most typical of compounds that are either inorganic or organic. So maybe an I or an O on that line next to each number. And so we'll have you pause the video here, and then for number 1, for instance, has a high melting point. If you think that describes an inorganic compound, then you'd put an I. If you think it describes an organic compound, you'd put an O. And again, just remember that it's the general rule of thumb for that classification. There may be exceptions, and we certainly aren't going to ask about the rare exceptions here. We want to get your take on how you're doing with the general rule of thumb. So pause the video here. When you're ready to check your answers, start back up, and we'll see how you did. Okay, so hopefully you did very well here. Looking at each of these, I spell out the whole word just so there was no confusion, but like I said, if you did an I or an O to distinguish, that would be great. So for number 1, hopefully you went with inorganic, has a high melting point. Now there are some organics that have relatively high melting points, and there are some inorganics that have relatively low melting points, but by and large, the inorganics tend to have the high melting points. I'll probably bring it up several times because it always comes up, but diamond is an example of inorganic carbon. It's just carbon, no hydrogen, and therefore it's not organic, but it is inorganic, and it does have a very, very high melting point. Looking at number 2, we have not soluble in water. That tends to describe the organics. The inorganics tend to be water soluble. The organics tend not to be. But as I've already mentioned, the alcohols, at least the low carbon chain alcohols like the ethanol that some of us enjoy, that's not soluble, or that is soluble in water rather, but even though it's organic. But it's an exception. So by and large, the organics are not soluble in water. The inorganics usually are, although of course they have exceptions as well. For number 3, has a formula. There we have it. That's the formula of propane. So there's carbons and hydrogens. That's going to be an organic compound. So that's the dead giveaway, is that you have the hydrocarbon bonding. And again, those hydrogens could be replaced by other atoms, but typically organics will have at least some carbon-hydrogen bonding and then some other atoms possibly as well. For number 4, has a formula of MgCl2. That's your typical inorganic compound, your classical ionic compound with a metal and some nonmetals in this case. For number 5, organics tend to be the ones that are flammable, and number 6, organics also tend to be the ones that are nonpolar. So hopefully with this classification scheme, you did pretty well with getting what tends to characterize more of the organic compounds versus what tends to characterize more of the inorganic compounds. If you're having trouble with this, reach out to me for help. Go check the end of the chapter, try some of those additional problems. There's certainly the homework set problems, but there aren't many on this particular topic, so look at the end of chapter problems or reach out to me for some additional practice problems if you're struggling with these concepts. So let's hope that learning check went well and you're doing very well with the idea of general property of organic compounds. Now let's talk about the bonding of the organic compounds, and let's talk specifically about the hydrocarbons, right? Chapter 11 here is going to go into the chemistry of the alkanes quite soon, but for now we'll just talk generically about hydrocarbons. And hydrocarbons are organic compounds that consist of carbon and hydrogen atoms. It's very self-explanatory, I hope. They have electron dot formulas that have 4 bonds on each carbon. All right, so they may not have 4 hydrogens because some of the carbon bonding can be with other carbons, but you'll have 4 bonds, 4 lines that you'll draw in the skeletal structures. So hydrocarbons with only single bonds are called saturated hydrocarbons. And we see here an example, methane. There's the carbon and the 4 hydrogen atoms coming together in our Lewis structure and Lewis electron dot formula, however you learned it if you didn't have me for Chem 141. And then finally, we can also represent that in what's known as a skeletal structure. or line diagram where we replace the two dots there representing that shared lone pair, or that shared pair rather, no lone pairs on this one, as a single line. So there we have methane, CH4, carbon with 4 bonds. In this case, each bond goes to a separate hydrogen atom. Methane is our simplest hydrocarbon, and it's also the one that if you're using natural gas for heating or cooking, that is the principal component. There's probably some ethane as well, but mostly methane, and it burns quite cleanly because it's such a small substance. All right, so there we have it, methane, our simplest hydrocarbon, made up of those 4 single bonds. All right, so that gave us a 2-dimensional representation with lines and letters to signify atoms. Here we have the 3-dimensional representation of a tetrahedral structure for something like a hydrocarbon, like in our example in the previous slide, methane. So VSEPR, valence shell electron pair repulsion theory, from back in Chem 141, General Organic Biochemistry 1, you learned about this theory, and it predicts that the best way to have a central atom with 4 bonding groups in 3-dimensional space is to have it arranged as a tetrahedron, right? You would think to do it in a square plane like it looked on the previous slide, but remember, then you've got all that space above and below the plane that's being wasted. You have repulsion between these shared electron groups, so you want to separate them as much as possible, and that's where the tetrahedron wins out in 3D space. So it gives a 109.5 degree bond angle, and it can be thought of as sort of a pyramid, right? If you want to think about it in terms of a 3D object that hopefully you've been over to Egypt to see, or at least seen pictures. And so that's what we have in the case of a tetrahedron. We can also see it as the ball and stick type model. Obviously there's no sticks in between the atoms, which is why C, that space filling model, is a little better representation of how we're sharing that electron density across those atoms. And then finally D, the expanded structural formula. I think I may have misspoken a couple of times earlier in this lecture and called it a skeletal structure. That is different. That's something that we're going to work into, but this is the expanded structural formula where we've replaced those 2 dots to represent each electron by a single line for the bonding pairs. Okay, so we show it in all these different ways, but really we tend to write it out like you see in D an awful lot. That's what we did in the previous slide, but just keep in mind it's really a 3-dimensional object, and you should be using 3-dimensional thought process as you're considering how these substances look and how they react to undergo chemical reactions. It doesn't take long to complicate this though, right? We had our simple tetrahedron of CH4 for methane. If we just go up another carbon atom into ethane, again the second simplest hydrocarbon, we have now each carbon atom bonded to another carbon atom and then to 3 hydrogen atoms. So each of the carbons is like a tetrahedral center, and then we're sharing those tetrahedra across the carbon-carbon bond. So we can show that in A with the tetrahedral shapes sharing, or we can look at it in the ball and stick formula. We can look at it in the space filling formula, or we can look at it on the flat 2D expanded structural formula. Again, that's the worst representation in terms of thinking about how it looks, but it's the most convenient in terms of being able to write it quickly and easily. So just remember, for this case, we have all single bonds. The carbon-carbon bond's a single bond. Each of the carbon-hydrogen bonds is a single bond. So we have free rotation. These things can move around each other. They're not stuck. And at room temperature is actually quite warm when we're thinking about absolute zero being minus 273 degrees Celsius. Room temperature, anything close to 20 degrees Celsius, is balmy compared to that. So we do have lots of energy at room temperature to deal with, and the way that these molecules deal with extra energy is to just move around and vibrate and get rid of that extra energy that they might absorb briefly. So there is free rotation around all single bonds. Keep that in mind throughout the course. We'll talk about double bonds soon, and we'll talk about the consequence of double bonds, but while we're nice and easy here in the hydrocarbons, when we're talking specifically about alkanes, everybody's tetrahedral in terms of carbon atoms, and everything is free rotation for those single bonds. All right, so before we leave this first part of chapter 11, let's have one more learning check. Let's see how you're doing with these concepts. So in this learning check, your task is to identify each of the following molecules as organic or inorganic. So we've got A, B, C, D, E. If you just want to either write the word or the letter that distinguishes the organic from the inorganic, pause the video here while you do that, and then start us back up when you're ready to check your work. All right, so hopefully you had relatively easy time with that. And C3H8 rather, the propane that we've been talking about as an example throughout this lecture is indeed organic. It's carbon and hydrogens, so that's classic organic structure type. For B, we've got carbon C7H14Cl2, so we've got carbon, hydrogen, and in this case chlorine, and we did say there are some other atoms that get involved here, and so that still falls into the realm of organic. For C, we have calcium chloride, so we've got some capital C's there, but none of them to represent carbon. So if we don't have carbon, we don't even have to think about it. It's definitely inorganic. Just because we have carbon doesn't necessarily make it organic. I already mentioned diamond is an example of inorganic carbon. The carbonates, if you remember things like MgCO3, magnesium carbonate, or CaCO3 from General Organic Biochemistry 1, that would be an example of another inorganic carbon. So just having carbon doesn't necessarily make it organic, although more often than not it will be in this course. But having no carbon means you will be inorganic without a doubt. Moving on to D, there's an example of an alcohol, methanol, right? It's based on methane, which was CH4. This time we're CH3OH. So that's our simplest alcohol, methanol. And because it is a carbon, hydrogen, and in this case oxygen, it falls into that scheme of your classic organic compound. Finally, the last molecule here, SiH4, silane, is an inorganic compound, although it does behave a lot like organic compounds. Silicon is the next one down in carbon's family, so it has a lot of similarities for a lot of these substances that are silicon and hydrogen compared with carbon and hydrogen. That's one reason there's a lot of work done with siloxanes, which are similar to chemically modify as the hydrocarbons or the organic substances rather. But again, it is different. It's not carbon containing, and certainly in this case we would say because it has no carbon, it's inorganic. Even though it does similar chemistry to some of the hydrocarbons, it's still an inorganic substance.